In this video, we discuss Newton's method, which is a technique for approximating the zero of a function when using the x-intercepts of successive tangent lines. So suppose that we've got this function, y equals x cubed minus x plus 1. Well, that's a cubic function. We can tell that it crosses the x-axis once. If we zoom in a little bit, we can see that that x value where the function crosses the x-axis is between -2 and -1. Now, we can infer because the y value at -2 is a negative value and the y value at x equals -1 is a positive value, that the function has a 0 between those two values. Even if we didn't know what the graph looked like, if we know what f of -2 is and we know what f of -1 is, and we can find that out relatively quickly by plotting those points. Let's say, well, the y value at -2 is -5. The y value at x equals -1 is +1. So the y values are changing from a negative value to a positive value. And we're dealing with a polynomial, so we know polynomials are continuous and differentiable on their entire domains. So by the intermediate value theorem, we are certain that there is a 0 of this function between x equals -2 and -1. We can actually see it. We can look at the graph and tell it's probably right there at that x value. Well, it's not that x value. It's that negative 1.325. The y value is 0 there. But you might say, okay, what if I couldn't just select that point on the Desmos graph? If I knew that that 0 was between -2 and -1, but I wanted to find it, how could I find it? Well, I could use Newton's method to find it. The first thing that we would do to find that 0 is draw the secant line through these 2 points. And the secant line is relatively easy to find. The slope of the secant is f at one endpoint, so f of -1 minus f of -2. So we're going to have -1 minus -5, so that's going to be 6, divided by -1 minus a -2. So -1 minus -2 is 1. So you have 6 divided by 1, which is 6. So the slope of the secant is 6. And then the tangent line, or excuse me, the secant line there just passes through this point, -1, 1. So the y value there is the function value at -1, which is 1, plus the slope of the secant, which is change in y over change in x times the change in x. And the change in x is x minus the -1, which is x plus 1. So if we graph that secant line, we see it. And we say, well, that secant line has a 0 that's very close to the 0 of that cubic function that we're looking for. So we can use that 0 of the secant line, or in other words, the x-intercept of that secant line, as our first approximation of the 0 of the cubic function on the interval from -2 to -1. So you say, okay, well, how do I do that? Well, I just set y equal to 0 and solve for x. Well, in order to do that, I would subtract f of -1 from both sides. I would divide by the slope of the secant. So I'd end up with this. And then to get the x by itself, I would subtract 1 from both sides as well. So I'll have -1 minus this function value divided by the slope of the secant. And that's going to be our first guess. So we're going to call that x sub 0. And that is -1.1667 approximately. It's -7 divided by 6. And if we plot that point on the curve, we see we don't actually have a y value of 0 there, but we have a y value of 0.597, which is a lot closer to 0 than either -5 or 1 was. So that's our first approximation of the 0. It's that x equals -1.167. Then you say, okay, well, how can I find another approximation? Well, at that point, I can create a tangent line and then find the zeros of that tangent line. So we'll say, okay, I'm passing through this point, x naught, f of x naught, where x naught is that 0 of the secant line. Then the tangent line at that location is given by the y value, is y equals the y value, f of x naught, plus the slope at x naught, f prime of x naught, times the quantity x minus x naught. So this is our tangent line now. I'm going to draw that in green. If I zoom in, whoops, I can see But that tangent line is very, very close to the zero, or the zero of the tangent line is very, very close to the zero of the original function. So if I want to find that zero of the tangent line, that's the x-intercept of the tangent line, again, I just set the y value equal to 0. I'm going to get rid of that earlier secant line now. On the equation of the tangent line, so I set y equal to 0. I subtract f of x naught from both sides. I divide by f prime of x naught, and then I add x naught to both sides. So my new x value, my new x approximation is the original x value, or the x value from the last approximation, minus this function value divided by the slope. And so I get that. And if I plot that point, that's the y value on our graph with the corresponding x value, which was the 0 of the tangent line, or the x-intercept of the tangent line. We see that our y value isn't 0 yet, but it's negative 0.13, so it's pretty close. So you say, okay, and we had this as our initial approximation. It was the 0 of that first secant line. And then we said, okay, at that 0, let's draw a tangent line and then find the 0 of the tangent line, which is just the x-intercept of the tangent line. You set y equals 0 and solve for x. Then we'll call that x value x sub 1 because the last one was x sub 0. So this is x sub 0, f of 0, and this is x sub 1, f of x sub 1. And notice that the difference between x sub 1 and x sub 0 is 0.188 approximately. So we're saying that, well, the difference between those two x values is still pretty large. It's larger than we want. Usually we want the difference between those successive x values to be pretty small. Like I'd like to see some like 0.00 something. So I will iterate again. I'll do the same thing. So I'm at this location. I'm calling this value of x x1, and I'll find a tangent line for x1, or at this location. So let y equal f of x1 plus f prime at x1 times the quantity x minus x1. So we have that as our tangent line there. You see it's tangent to the curve. You say, where does that intersect the y-axis? Well, it's almost indistinguishable from the actual 0 of the function. It intersects the y-axis, or excuse me, the x-axis at looks like negative 1.3255. But again, I set y equal to 0, subtract f of x1 from both sides, divide by f prime of x1, and then add x1 to both sides, and I'll call that x2. And then I'll plot that point. And check out the y value. It's negative 0.0034. Very, very small. Still not 0. And the difference between x2 and x1 is this 0.0288. So it's still small. We're off by less than 3/100ths, but I'd like to be off by less than 3/1000ths. I'd like to be accurate out to the third decimal place. So we'll iterate again. We'll find another tangent line using x2 this time. So evaluate the function at, or we'll evaluate, or we'll find the tangent line at that location. We'll have y equals the original y value, so that's f of x2, plus the slope at x2 times x minus x2. And then we'll call this x value x3. That's the next x value we're looking for, and we'll set y equal to 0 and solve for that x value. So we subtract f of x2 from both sides, divide by f prime of x2, and then add x2 to both sides. So we'll have x3 equals x2 minus f of x2 divided by f prime of x2. And this is what we get. And that is pretty damn good. It's negative 0.3247. And the y value is considered to be 0. So now Desmos is saying that's close enough to 0 for us. That is the 0 of the function. And if we look at the difference between x3 and x2, we have 0.000786. So we are accurate out to the third decimal place at least. And then that fourth decimal place might be off by a little bit. So this is definitely at least negative 0.3247 or negative 1.324 or 325 is an excellent approximation of the zero of the function. Okay, so in general, you say, how does this work? How do we find the zeros of the function? Well, if you look at the graph of the function, you say, I'm pretty sure that there's a zero on this interval between -2 and 2. Why? Because when I graph the function, I can see it. I'm going to try to get rid of that point that I plotted earlier. You say, I know that there's a zero between here and here due to the intermediate value theorem. How can I approximate that zero? Well, I find a secant line. I find the zero of the secant line, which is just the y-intercept of the secant line. I use that as a guess. And then at that x value, I create a tangent line. And then I find that where the tangent line intersects the y-axis. And then I use that x value as a guess. And I keep doing that until the difference between successive x values is small enough that I'm happy with my answer. I'm saying the error is small enough so that as far as we're concerned, like that's good enough for us. That is the zero of the original function. And it turns out with this example, we only needed to do this 3 or 4 times. The first time we were using the secant line, and then the next 3 times we used the tangent line to approximate the function. And each time we found out where that secant line or tangent line intersected the x-axis, and we said that is our new guess for what that zero is. And it only took 4 iterations for us to be within 0.0008 of the actual value of that zero of the original function, which is negative 1.325 according to desmos.com. So you say, how do I do it again? In general, the equation of the nth tangent line is y equals the function value at the last x value. So that's the y value from the last time, plus the derivative at the x value from last time, times the quantity x minus the original or the x value from the last time. And then you set this y equal to 0 and you call this x sub n, and then you solve for x sub n. So if this is 0, you're going to subtract this from both sides, divide by this, and then add this to both sides. And you will get x sub n is equal to the last x value minus the y value at the last x value divided by the derivative at the last x value. Now you might have problems if the derivative is undefined. Of course, if the derivative is undefined, you can't do this. And of course, if the derivative is 0, you can't do this. You've got a derivative at the last x value in the denominator. And the advice in the textbook says, if that happens to you, you've got some point in the sequence where the derivative or sequence where the derivative is 0, just choose a different x value to start. I like to use that x-intercept of the secant line. I think that's a great approximation, a great place to start. But if that leads to one of these problems where the derivative is 0 or the derivative is undefined, then you might choose a different guess. But it's good to just look at the graph of the function and guess based on the graph. You say, here's the 0. I know to the left of that 0, the y is negative, and to the right of that 0, the y is positive. And I can pick a couple of integers, x equals -2 and x equals -1, and evaluate the function there and see that I've got different signs, a negative function value on the left and a positive function value on the right. And then I say, because the function is differentiable and continuous by the intermediate value theorem, there has to be a 0 in there. Say, what is it? How do I find the 0? By using these tangent lines. And you don't actually have to think through that process of using the secant line and then successive tangent lines to find the next x value. But I personally like to know where those formulas come from. Like we could blindly just substitute values into this recursive relationship for the x values, not knowing where it comes from. That would get us a table of values that would eventually lead to the solution in most cases. But we wouldn't really understand sort of what it means and why it should be true. By describing this here for you, I hope you understand now why we should use a formula like this to approximate the zeros of the function. So that's it for that. The introduction to Newton's method. In the next video, we'll actually apply Newton's method to a particular function, and then we'll illustrate everything on Desmos.com once again.